So now we go into much more complicated algorithms, sorting algorithms. So sorting algorithms are needed in order to be able to execute or apply the algorithm we just saw. This only works if your phone book is already sorted. So you can see why sorting algorithms would be important. The first sorting algorithm we'll look at is called insertion sort. So I could define it for you or explain it, but I think it's better to see it in practice. So let's look at what Wikipedia has to say, and let's look in particular at this applet here. So here we're trying to sort this sequence of numbers. And what Wikipedia does, or what this applet does, is that it compares the initial list that is already sorted, what is in black here, with a new entry that is selected in red. And the new entry progresses from the left to the right. So now we compare 1 with what is already sorted, and 1 is smaller than 6, 1 is smaller than 5, 1 is smaller than 3. So we insert it here. Now 8, we compare it with 6, and the comparison is immediate. It's bigger, so we just leave it in place. Now we do 7 with 8, and 7 gets inserted before. Now 2, we'll lift it and compare it in turn with each of those and move it to the right up until the comparison with the entry in black means that we should insert it. And finally, 4 is lifted, compared with all the previous ones, up until we find the right place for it, and we insert it. So this is an insertion sort for you. So what does it do? For every input that is coming from the right, every one of those red boxes, it was inserted into the current sorted sublist in the appropriate place. And how I've just illustrated with this little applet, it was lifted and then each of the, so saved somewhere else in memory, and then each of the sublist, the current sorted sublist, which was in black, was moved one to the right up until we found the right place for the number that we had saved, and then the number that was boxed in red. And then we insert that number. And we do this for every input, so every one of the red boxes, all the way until we're done. Okay, so what's the worst case complexity? Well, in order to sort in this way, we have to have a sorted sublist of size 1 less than the one we currently have. So this means that we can break down nicely the complexity for sorting a list of size n into the complexity for sorting a sublist of size n-1 plus the number of steps required here to insert the last input into the correct place. And if you look carefully, this requires n-1 comparisons in the worst case. So in the worst case, I have to compare this red box with all the other black ones up until I'm satisfied that it actually comes all the way to the beginning. So I've given you a hint already of an interesting question is when is the worst case achieved? So for which initial sequence of numbers is this worst case actually achieved? In any case, we now have a formula for f of n that relates f of n to fn-1. So if I use this, I can say that f of n is n-1 plus f of n-1. But then I iterate, and f of n-1 is n-2 plus f of n-2, and so on, all the way to summing to 1. So f of n is the sum from 1 to n-1. And that you can compute is exactly equal to n times n-1 over 2. So if you need a little trick to compute this, you can pair up the numbers here, 1 with n-1, 2 with n-2, 3 with n-3, etc. And you just need to count how many pairings you have like this, because each pairing, the sum is exactly n. In any case, what we get here is n squared over 2 minus n over 2. And if we remember that the lower order terms don't matter and the fraction does not matter, the constants in front don't matter, we see that this is big O of n squared. So the step complexity in the worst case is going to be O of n squared for an insertion sort. Now we go for merge sort. So merge sort is slightly better. What it will do is it will divide the list into sublists of length 1, and repeatedly merge the sublist of similar size until there is only one left, which will be sorted. So, time for another Wikipedia example. So I'm now on the Wikipedia page for merge sort. So you can see the sequence that needs to be sorted, and what Wikipedia does is that it splits it into subsequences of half the length, and then a quarter of the length, an eighth of the length, and so on, up until you have subsequences of length 1. And then it recombines it into subsequences of length twice as big. And each time this requires just one comparison, because 2 and 4, for instance, here need to be compared. And now we have groups of size 2. And we'll try to make groups of size 4. So we'll compare 1 and 5, 3 and 5, and then we're left with 5 and 6, which are bigger. Here we'll compare 7 and 2 is first, 7 and 4 is first, and then 7 and 8, no more comparison to do. And finally, we now try to merge this all two sublists into one big list. So we compare 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 7, and 6 and 7, and finally 7 and 8. And we have our sorted sequence. So now we compute the worst case complexity for merge sort. And again, you should wonder, when is this achieved? So when is this worst case complexity achieved? For which input of cards is this worst complexity reached? Okay, so let's make a simplifying assumption. Let's assume that n is equal to 2 to the k. And if that's not the case, then you should add more cards so that you get to a power of 2. Okay, so if we have 2 cards, how many steps are required to sort it? Well, that's easy. Only one step. We just need one comparison. Okay, what if there are 4 cards? Well, what is required from what merge sort does is that it will split those 4 cards into 2 groups of 2. And each of those groups of 2 can be sorted, we just saw it, by doing one step each. And then it requires those 2 groups of 2 to be merged into one group of 4 that is sorted. So how many comparisons are needed for this? Well, here is a trick. In the worst case, I'll need one comparison for every insertion I do, except for the last one. So in other words, to compare those all those in order to sort them into a sequence of 4, I'll need to do 3 comparisons. With the first one, let's say taking this one, the second taking this one, and then I'm still left with 1 in each, and I have to compare them to decide how to put them. And this is the general situation. If you do the comparisons in such a way that you're left with 1 in each of the 2 groups at the end, then you will need exactly the length here minus 1 comparisons. Okay, so in summary, the number of steps required to sort those 4 cards are 2 times the number of steps required to sort the subsequences plus the number of cards, which is 2 to the 2 minus 1. And similarly, if you have 8 cards, well, you have to sort 2 groups of 4 cards and then do at most 7 comparisons to figure out how to merge those 2 groups of 4 into one big group of 8. What about if you have 2 to the k or n cards? Well, in that case, you have to do 2 times f of 2 to the k minus 1 plus 2 to the k minus 1. Okay, so this is the beginning of computing the complexity. It will become harder. So to simplify, I'll just say that this formula here, I'll just ignore the minus 1. This minus 1 is actually not important when you compute the complexity. You can prove that, and you should probably prove it as well. So let's see. F of 2 to the k is equal, I just said, to 2f 2k minus 1 plus 2 to the k. And I ignore the minus 1. Okay, but obviously this is a recurrence relation, so this f of 2k minus 1, I can use this exact formula where I replace k by k minus 1. So this is going to be 2, and I write this, let's say I write this 2 to the k first. So I write 2 to the k plus 2 times the same thing, but where I replace k by k minus 1. So this would be 2f 2k minus 2 plus 2k minus 1. Okay, very good. But I can obviously still apply the recurrence here. So I'll have 2 to the k plus 2 times 2 times 2 times f of 2k minus 3 plus 2k minus 2 plus 2k minus 1, and so on. So that's very good. But if I look carefully, I realize here there is a 2 to the k, and here, thanks to this multiplier there, I have another 2 to the k. And here, thanks to this multiplier here, I have another 2 to the k, because this here is multiplied by 2 and multiplied by 2 again. So this is really 2 to the k. So in other words, if I expand this whole product, I'll have 2 to the k plus 2 to the k plus 2 to the k, etc. And I'll extract a lot of those. So how many of those do I extract? Well, if you look carefully, you will see that the number I extract is going to be exactly k, or within 1 of k, let's say. And the reason is that each time I extract a new 2 to the k, the exponent here decreases, and it will decrease all the way until it reaches an exponent of 1, which gives me f of 2 to the 1 is 1. So in other words, I'll have k times this, so the complexity should be k 2 to the k. And I've ignored constants that are not important when I do asymptotics, when I compute this slim soup. But this constant here is important because this constant is actually not a constant. It depends on n. So k is actually log in base 2 of n. So what I've obtained here is log in base 2 of n times n, because 2 to the k was n. Okay, and now I'm ignoring the constant, the fact that the logarithm is in base 2. I could just take it natural logarithm, I would get the same thing. So this here gives me the conclusion that in the worst case, the complexity is on the order of big O of n log n, where n is the size of the list. So again, a good exercise for you is to try to picture what should be the initial ordering of the deck of cards in order to achieve this worst case scenario. Okay, so this was a brief introduction to complexity. Obviously, there is a huge array of problems that are interesting in complexity. In particular, the one I mentioned, P equals NP. So I won't go in more detail here, but if you want to do one of your projects on P equals NP or P different of NP, so this conjecture, that would be very interesting as well.